Well, hello everyone. This is the first talk of the series in machine learning that Rena and Joanna are organizing. So they asked me to talk about something about machine learning, and actually I did my master's thesis on a technique in machine learning called random forests, and I wanted to explain you the basics of how a random tree works and an idea I had on how to improve it. So, first of all, I want just to briefly introduce myself and what I was working in. So my name is Roma Domena, and I'm a PhD student in the Applied Math department here at IIT. This is my first year, so I still didn't specialize in anything, but probably I will work on something in either statistics or probability or machine learning. I still don't know. But 2 years ago, I was doing my master thesis at the Meteorological Institute of Technology of the Netherlands, and I had to predict the wind speed in Europe. So here you can see more or less the domain with which we were working, which is all that region, circled in red. And here I plotted the 3,700 meteorological stations we were working with. And we were dealing with the following problem. We had a model based on differential equations that the physicists created that predicted the wind given some initial condition in the atmosphere. And we realized, when meteorologists realized that this model was not good enough for predicting the wind speed, so they wanted to make a statistical refinement to improve it. And this is where my work started. Okay, here you have different details of the model that I will not explain, but that's it. They had a physical model that predicted the wind. It was not good enough, and they wanted to refine the predictions in all these points in Europe. This is one of the meteorological stations that was collecting the data every day. Okay. So this technique that I used to refine this prediction is called random forest. Maybe some of you already know what it is. But in case you do or you don't, I'm going to try to explain it everything from the beginning and very simple. So the first thing to say is that a random forest is composed of trees, like the ones you can see, and they are rather turned upside down. So if you want to understand the model, you have to think of a tree that is turned upside down, because the data is going to come from the top, which would be the root of the tree, and the predictions are going to stay in the leaves of the tree. But I'm going to explain this more precisely. So the way it works is you have your data on the left. I have here my data, which are different meteorological variables measured in 3,700 locations in Europe. And for each of these meteorological variables, you have different values. For instance, we can have the elevation of each meteorological site, the latitude of each meteorological site. All these are variables that the statistical model will use to predict. And then you have, in my case, we have the most important variables, which are coming from the physical model, which is the prediction from the physical model that we wanted to improve, which is called mean. And this is like the error of the physical model, which we also took into account to make the refinement, which we call standard deviation. So this is more or less the data set we're using. This is the geographical sites where the variables were measured. And what we want to do with this random tree, or this post-processing, or this refinement model, which is a machine learning technique, is to give this input data and get something out of the leaves of the tree, of the forest. Yeah, this is an intuition of how to think about it, but I already explained this. Okay, so in order to understand how a random forest works, you just have to understand how a tree works first, and then once you get how a tree works, a tree makes a prediction based on your data. The data goes through the tree, let's say, and once it reaches the leaves, it gives a prediction. So once you have a prediction for one tree, you add up, let's say, 400 trees, which was what I was working with. My forest had exactly 400 trees. And then you kind of average the predictions for each tree, and then you get the prediction of the random forest. So everything lies in understanding how a tree works. So here on the left, I plot the intuition of a tree, and on the right, I plot a tree I got from my data set, limiting very much the amount of nodes. What I call a node is every time there is a split, a branch, let's say. Some people call this a decision tree, but in my lab we always call it a random tree because there is some randomness that I don't want to explain now. But you can call it however you want. I will explain how this one works. So the way it works, first I will explain how it works, and then I will explain how to create one. Okay, so the way it works, you put there some data, and at every split, what the tree does is it takes a look at the data row. The data row will contain a variable called mean. If this data row has the variable called mean that is bigger, in that case, than 6.24, your data row will fall to the right. If the variable mean for that data row is smaller than 6.25 meters per second, it will fall on the left. Once you go to the second split, it will take a look in that data row that you are introducing to the tree, the variable called elevation, which is the elevation at which the wind speed was measured, or the elevation at which you want to know the wind speed. If you want to know the wind speed for the IIT, you just have to measure at which point you want to compute the wind speed, that you have to measure the elevation, and then you will be able to make a prediction. So in that case, oh, you don't hear me? Do you hear me or not?
No, it's good for the recording.
Oh. Do I have to put this on, or what should I do?
Test the mic.
Hello?
I don't think it's on.
There's like a bell with the bar.
Oh, so what should I do?
Just clip it out.
Okay.
Alright, what's this?
Well, I don't know if it works, but I will keep talking. Okay. So how does a tree work? So we want to predict the wind speed for some place, let's say the IIT or Mumbai or wherever you want. You have to have several variables that give you information of that site. I already explained the first split, so in the second split, if you are computing it at the IIT, probably the elevation from the sea level will be smaller than 8 meters. So for that data row, you take a look at the variable elevation, you read what is the value. If it is more than 8.07, it will fall to the left. If it's bigger, to the right. In the IIT, for instance, elevation would be smaller than 8 meters. It would fall to the left. And then you have to read the variable SD, which is the wind speed prediction of a physical model. In that case, I don't know which was the physical prediction. This would be the physical error, sorry, but it's plausible that it will be smaller than 1.3 meters per second, because 1.3 is already a big error in predicting the wind speed for physical models, because they are quite precise. So we could say it will fall on the left. So you would get to this point, and once you get to the leaf, this is a leaf. One of the leaves of the tree would correspond to these last values. This is telling you exactly the wind speed that the tree is predicting for that data row. So that you put the data row in there, you follow the splits according to the values of the variables of your data row, and once you get to the leaf, you have the prediction for your predictant. In my case, the predictant or the variable that I want to predict is the wind speed. So the tree would tell me, in this case, that the prediction for the information I put is 8.79 meters per second. Well, that's how it works. Okay, I just wanted to focus in case someone didn't see the last number. Well, I wanted to zoom in. Okay, well, so this would be an example, again, for how it works. I already explained it, so I will go very briefly through this one. So here you can have, maybe you want to know the wind speed for Mumbai. I took a look today at Google which are the meteorological variables that I have in my data set for Mumbai, so that my model has. Mumbai, we can say that Mumbai has a latitude of 19 degrees, a longitude of 72.9, an elevation of 14 meters above sea level. And then I kind of made up the last two because the physical model I was using didn't work in India, only in Europe. But I assumed, let's say, what I did is I took a look at you have an institute in India which is called the Baba Atomic Research Center. Well, I don't know if you know about it, but I took a look at it, and I just took the mean wind speed in Mumbai and the standard deviation. Okay, so if you want to know the wind speed for Mumbai, let's say tomorrow at 2 p.m., the way the tree would give you that wind speed is in the following way. So this is what this data row would follow. So in the first split, the tree will look at your data input from which you want to know the prediction, okay, from which you want to predict the wind speed. And okay, the mean is smaller than 6.4, so in the first split it will fall on the left. Then the latitude is, oh, I made a mistake here. The latitude is smaller than 48.5. Okay, well, let's assume it was bigger and I just made a mistake. If the latitude was 50, for instance, it would fall to the right. Then you would take a look at the mean, which is 2.4, and it will fall to the left again because it is smaller. Then you would take a look at the elevation, which is 14 meters, which is smaller than 744 meters, then it will fall on the left. Then the elevation is checked again, it's bigger than 1.29 meters, it falls to the right. Then finally the longitude is checked, and it's, in this case the longitude is 72 degrees, it's bigger than 6 degrees, then it falls to the right. And then you get a final prediction, in this case for Mumbai tomorrow, according to the variables I put in, of 2.17 meters per second, which is a very small wind. Well, this is kind of how it works. I don't know if everybody understood it, I hope so, but you can ask me questions whenever you want. But now I will explain how to grow one, which is where my idea was. Okay, here I have another data set. This is the New York temperature and solar radiation and wind. These three variables mixed together. And what I want to know, now I want to classify the temperature, so according to the wind and to the solar radiation. So I want to kind of find a pattern. So I have these dots, red and blue dots that you see, and I want to know if I can kind of say in which region I have more red dots and in which region I have more blue dots. That's kind of what a tree wants to do, to classify your data and then make predictions once you have classified the data. So what I show so far is once I have already classified the data, once I already have the tree, how does it work once I put a new input? And now I will show you how to create this tree, how to start from 0. So starting from 0 means starting just from these blue and red dots and having to grow the tree. Okay, very fast. In order to grow the tree, as we saw previously, you have to, the meaning of growing a tree means just create some splits in each variable so that your data will be splitted at every time more and more. So if here I have this initial data set, the first thing I should do is to make just one split. One split, once I show you the data set like this, just translates in 2 dimensions of just drawing a line. And then the data will be split between the points that lie on the right-hand side and the points that lie on the left-hand side. I run again in R, which is the computing language I use for these statistical models. I grow this tree using the package rpart. And the first split that the program did is this one, which seems quite reasonable. It can only do splits that split one variable in one precise value. So you can only have splits that are like either the values are smaller than, let's say, here 80, or the data points that are bigger than 80 in terms of the solar radiation. So the split can only be like in the vertical or horizontal if we have 2 variables. In this case, I think everybody would have shown the same split. You know, you see more blue points here, and here you see more red points. So probably people would try to split. In order to classify the data set, the first split I would do would be somewhere here as well. So that's kind of reasonable what the tree is doing. And if you follow the iterations of the tree, this would be like the second one it would do. So it would find another variable. These are the splits I'm considering. Another variable, in this case, now it will take the wind, must be smaller than 11 meters per second or bigger. And it keeps doing the splits like this. Okay. Once you follow all the splits, you get something like this. Why does this line not reach that point? Because the splits are recursive. So once you do a split, this is the representation of that data. So we start from the beginning. Okay, in the beginning, the first split was solar radiation is either smaller or bigger than 80, which corresponds to this split. And all the points that fall on the left, so all the points that lie here, are kind of blue. So the algorithm says the standard deviation is small enough as to stop and as to not split this further, not classify it more. This is a variable which is called tolerance, and in your algorithm you can set it to whatever you want. In my case, I set it to 0.001, and then it stops in this case. This is blue enough, so the tree will not split further, this node. But the other node, which where all those points are not yet well enough classified, so it will keep doing it. If the solar radiation is more than 80, yes, all these blue points, then don't split it more. And it reports the average temperature, which is 21 degrees Celsius, which is kind of, not cold, but more like moderate temperature. And then all the points that fall on the right, so that have a solar radiation bigger than 80, are still quite mixed. Their standard deviation is still quite large, so they will be further classified. So the second split, which I also showed you before, which is wind either bigger or smaller than 11 meters per second, which corresponds to this line, is made. And why does this line not reach this point? Well, because it's only splitting all the points that satisfy a wind either bigger or smaller than 11 on the right-hand side node. So that's why the line only reaches to this point. The points falling here belong to another node, so therefore they are not split well. And this is how the tree is grown. By doing these splits that translate to these instances, you are splitting the data, and then every time you do split, you report the average value of the predictant, which in this case is the temperature, and every node. So the 26 that you see at the beginning is the average temperature of all the data set. And once it is split, you have on the left-hand side what we expected, because it's more blue, a chiller temperature, in this case 21 degrees Celsius, and the right-hand side, which was all this thing, which contains a lot of red dots, a kind of hot temperature of 27 degrees Celsius. So it kind of makes sense, and it seems useful. Well, at least that's what I hoped to transmit to you with this example. And this whole tree is grown, and then you can go until the end. Okay, so now, at least from my point of view, I explained everything I wanted to explain you about how a tree works. Now I will focus on how to improve this a bit, because the thing is I didn't like this. Yes, sorry.
Did you have an algorithm decide these points to split for you?
What? Of course. I mean, I didn't do it by hand. No.
That's what I just wanted.
No. I mean, you can do it. There are, I think, 200 points. So no, there is already the algorithm. So if you use R, I don't know if you use R, or you know what is R, but if you check the R part, if you check this, sorry, my handwriting is very bad, so this is an R. If you check this package, that's the one I used to grow this, and also to plot it. And this is for growing a tree, and that's what I used. A regression tree, it's called in this case. And yeah, so I didn't do it by hand, no. Does it look ugly? Do you think I was doing it by hand because this doesn't look nice? Okay, well. Yeah, I don't know if you understood it, but I tried my best. And now I want to explain some improvement I wanted to do. Because, let me check something. Okay. Yes. Okay, what's the problem? I will first show you what I don't like, which is this. Then I will explain what to improve. So, I mean, I don't know if maybe some of you like this, but that's actually one of the real trees from my data set. This is one of the 400 trees that formed the post-processing model that we used in the Meteorological Institute of the Netherlands, and that now they use to refine the wind speed predictions. So this is actually what reality is, you know. This is, once you grow, at least in my case, the machine learning model, usually nobody wants to take a look at what is grown. They just make predictions, the computer knows what it's doing, so nobody really takes a look at what is going on there. But I decided to plot one of the trees, one of the 400 trees that compose that model, and see what is going on, because what many people don't like about random forests is that, okay, it gives very good predictions, but nobody knows how, you know. Nobody knows why when you put a new data input, the wind speed is very close, you know. If you have a parametric model like a linear regression, it's really easy to understand a linear regression, how it works, or yeah, a linear regression with only 2 or 3 parameters. Then you have the slope, and if the slope is bigger, it means maybe the variables are correlated or not. But here you cannot say anything about either variables are correlated or not, because, yeah, every variable is in the splits. So I try to paint every predictor in a different color. So one of them are orange. Another one, I think its longitude is red. Another one is pink. But it's really difficult to get any relationship between the predictors if you get a tree like this. Not to say if you get 400 of them, which are all different, and you issue a prediction with this, which is the average of them, you know. So even if this looks big, when I put a data input in there, it would end up in only one of the nodes. So you might be scared, but once I put a new data input, only one of the leaves, only one of the leaves will be used to make a prediction. But for every different input, it may fall in a different place. So that's what I didn't like, because I saw that's too complicated. I mean, I cannot say anything about the relationships of between the variables. Like in this smaller data set, which I put, here, once the tree is grown, okay, you can maybe say something. You can say in this region, and this region, it's kind of red. And then you take a look, and probably it's like 30 and 30. So these two regions are equally hot. So what you could say here is that if solar radiation increases and wind is low, you know, the temperature is kind of high. And if the solar radiation is very small, regardless of the wind, the temperature is kind of low. So you can still say something, which is what I think researchers want to do, right? We want to say which are the relationship within the variables. We want to understand better our data. And with a small data set, the tree still means something. Or with a small tree, I think that's better, you can still say something about the variables. But once you have this huge thing, you know, there are so many splits that you cannot say anything. And that's what I didn't like, and that's what what I tried to improve. So my idea of improving this was mainly of making the splits less simplistic, more complex, so that in one split, more decisions will be made, and therefore we will not need many splits in order to issue a prediction. One of the ways to get this intuition was that I realized that this tree is actually having too many splits for predicting the same. Because you see these different colors. There is light blue here and dark blue here. So I also put different colors for the wind speed. The wind speed is the predictor. The lower the wind speed, the lighter the blue. And the higher the wind speed, the darker the blue. So this means that actually all these leaves here are predicting pretty much the same wind speed. It's just that they are messed up with many splits, according to the algorithm. And all these ones are issuing a kind of high wind speed. And we can see that who's responsible of this? Well, mainly the splits in the top. Because, for instance, once that split in particular, because once your data input falls on the left, and on that split, regardless of where it goes afterwards, it will have a pretty much low wind speed, you know? And here, kind of the opposite. If your data input in that second split falls to the right, it will have a pretty much big wind speed prediction. So that's why I thought that we had to find a new way of doing these random trees or decision trees, a way of improving these splits that will detect this before, and we will not need to make so many predictions. Well, and the way I thought about doing this is of not considering only horizontal and vertical splits, but considering also diagonal splits that maybe could enable the algorithm to detect different patterns that otherwise take many splits to detect. For instance, here, in order to isolate this bunch of red dots, you need 1 split, 2 splits, 3 splits, 4 splits, 5 splits in order to isolate this group of red dots. And in the way, you separate 2 regions that are equal, which is what I want to avoid happening, which is this region and this region. These 2 regions have the same average temperature, which is 30 degrees, but nonetheless, they lie in different regions. So that's kind of, maybe the name is overfitting. I think that's the name. So I wanted to avoid this overfitting. The overfitting is extreme when, your data set is big or the tree is big. So my idea, which may not work, but I'm trying to work on it, was to allow splits that not only look at one variable at each time, but that look at combinations of 2 variables and up to 3 combinations of variables at each time. In other words, this is the formulation, but in other words, what I was looking for is that at each split, kind of convex bounded region could be isolated. In this case, it's a stupid region. It only contains 1 dot, because I'm still developing this algorithm. But my aim would be that, for instance, in just one split, a bounded region here containing a lot of red dots could be isolated, and therefore you would avoid, or you would save the algorithm from doing many splits, many iterations that are kind of redundant. Well, and that's my idea. I'm working on it, but I still don't have, I have not finished or anything. I still have many problems. Like now, my algorithm only isolates single points. The other problem I have is how to choose these lines, because there are so many different combinations that the computer, will take forever to consider all possibilities. The current algorithm of random trees or random forests is very fast because it only considers splits that are either vertical or horizontal. But my idea, even though it might be nice, has the problem that if you consider all possible directions and all possible intercepts for the lines, there are so many combinations that now the problem is find a smart choice of lines, possibly a finite amount of them, that kind of span all your domain in a very varied way. That's it. So that when you consider these convex regions, you have enough convex regions to consider as to classify your data in a fast way. This is the, I actually developed already this algorithm using these convex splits, and I used it in the same data set, and I got this tree. I did this myself by hand, not the algorithm, but the tree, because I still didn't program any function that automatically draws this nice structure. So I drew it myself from what my algorithm got. So it's kind of the same tree as the classical random forest tree, random tree. In this case, so that means it's not that bad, and that gave me hope to improve it because I just program it in 1-2 days. It's not very long algorithm, but I was happy to see that the tree it created had the same amount of branches and nodes that the classical one in this random data set. I expected maybe to have done something wrong and have here many nodes, but I thought this gave me hope because even if it's still not improving the classical one, it's already equally better in that data set. Okay. Well, and now this is even beyond what I wanted to say, but now here I'm just trying to explain the detail of how choosing all these lines that I was considering. So my trick in that data set is I only consider 10 lines, these 10 lines, and then I consider all combinations of every 3 of them. So for instance, this one would be a combination. So these 3 lines would, if we combine these 3 lines, we would obtain the combination, which is this shaded region. And if you consider all 3 subsets of this set of 10 lines, you get many different regions to consider. Some of them are, all of them are all of them are convex, and all of them focus on different regions of the domain. And that's what I used in order to create my splits. And that's it, actually. So it was kind of short, maybe, but that's what I wanted to say. There is nothing more. And before you ask questions, I also created kind of by myself the tree that I showed you before, the first one. So this one, in a simplified way, because I didn't have enough time to create all the splits, but I just created the main ones, and I tried to draw them here with a pen what every split represents. And here on your left-hand side, you have what would be the training data set. So in order to grow a tree, as I showed you, first you need some data that you have to classify. So this would be that data. Every dice is a data row from my real data set, and I draw every variable and every value it has by hand, if you want to take a look. And here would be the verification data set, or the predictions you want to make. So one of them could be Mumbai tomorrow at 2 p.m. And then you throw it down the tree, and it should fall somewhere. And I didn't put that, but each column has a different wind speed prediction, and it would tell you, for instance, if it falls here, that the wind is going to be 2 meters per second or whatever. This was just, I tried to represent the tree in this way, but it's hard. Well, especially because the dices don't fall where they should. You know, if here the latitude is 48 degrees, then it goes, and I don't know if it went in the right place, but probably not. Oh no, yes, it did actually, because here the latitude is 48. Ah, no, it didn't. Yeah. Well, so that's the problem, that once you do it physically, it's more difficult to make it work. Well, that's it. If you have any questions, you can ask. If you don't, you can eat the pizza.
Okay, thank you guys for coming. We have our next talk on next Thursday by Professor Sarah Zellenberg. She's going to talk about gradient descent and neural networks. If you guys are coming, you can bring your laptop. She said there will be some sort of interactive